Hi guys, and welcome back to part 3 of our deep dive into the Telum, our newly released rear shock. Here at Vorsprung, we're excited to bring something truly unique to the world of suspension. If you care about your suspension performance, or even if you're just a massive bike nerd, I think you're going to really love this. If you're a bike shop or suspension workshop, you'll be absolutely stoked to see just how easy we've made it for you to put your customers on an absolutely dialed setup. We're going to dive deep into the technology and design features that make the Telum truly special. So what are we talking about here? It's called Rapid Revalve, our patent-pending technology found exclusively inside the Telum, our new coil shock. For the first time ever, you can directly adjust the force versus displacement characteristic, also known as the stiffness, of the damper shim stacks without requiring a rebuild, rebleed, or even repressurization of the shock. No oil is lost, there's no mess, and the whole process is simple and elegant and takes just a couple of minutes. First of all, for anybody to really understand the impact of this and be able to believe that we aren't just marketeers who are full of shit and hyperbole, we need to understand what a shim stack is and how it works. For those who aren't familiar, a shim stack is a stack of flat metal disc shims held against the face of the damping piston, covering the oil ports in the piston. These together comprise an assembly called a valve, and the configuration of the shim stack is often referred to as the valving, since the number, size, and thickness of shims in the stack can be reconfigured to fundamentally alter the most important characteristic of a damper. That is, the resistance force versus velocity curve. We call this reconfiguring process revalving or reshimming. As oil is pushed through the valve by movement of the damper, the shims become a tiny leaf spring, flexing away from the piston and opening up a tiny aperture through which the oil can flow. The faster we try to force oil through the piston, the more resistance the small flow aperture provides, which in turn means higher oil pressure acting to flex the shims away from the face of the piston, which in turn means a larger aperture for oil to flow through. There are plenty of variations and exceptions, and we won't try to cover them all here, but within typical operating limits and low-speed circuit configurations, the end result is quite a linear relationship between the oil flow rate, meaning the damper velocity, and the amount of pressure drop over the valve, or the damping force. Long story short, the stiffness of the shim stack is the primary factor determining the gradient of that curve, at least in terms of determinant factors that can be altered without designing and machining whole new parts. When people talk about the tune of a shock, i.e. light, medium, or firm tunes, it's generally the shim stack configuration that is being indirectly referred to. Typically, a suspension manufacturer or tuner sets the shim stack configuration to what they think will probably work best, given the information they have about the bike and the rider. If this is happening at the OEM level, that means they know what the frame's kinematics are, and perhaps roughly how tall you are based on the size of the bike. But other than that, they need to try to predict who you are, what you weigh, where you ride, how you want it to feel, how strong you are, whether you like fast, slow, firm, soft, etc., when realistically they have no way of knowing these things in advance. By contrast, the Telum is tuned specifically for every bike and rider combination, individually. And if for some reason you don't like the tune you get, or you just want to experiment with something different, with Rapid Revalve you can change it yourself in just a couple of minutes, rather than having to fully rebuild, rebleed, and repressurize the shock, which is typically an hour or more's work even for an experienced professional. For serious races, this is a real advantage, because there's far greater tuning opportunity accessible within the time constraints of a race weekend with the Telum than with any other shock. So why can't this just be done with external adjusters? Well, we need to understand exactly what the external adjusters are and how they work. Typical low-speed adjusters are needles that simply adjust the size of an orifice, which provides most of the hydraulic flow area at low speeds when the shims have an open fire. This orifice doesn't vary in size during use, only when you turn the adjuster. Obviously, since the aperture for oil to flow through doesn't vary, this doesn't behave like a shim stack. Instead, you get a quadratic relationship between flow rate and pressure, which in effect means that as speeds increase, it chokes up and handles a smaller and smaller proportion of the total oil flow volume. High-speed adjusters are more complex and more varied, but the most common variants you'll see adjust a spring preload on the outside of a shim stack or on a poppet, holding it closed until the spring force is overcome. This effectively offsets the damping curve upwards, but with comparatively little or sometimes near zero effect on the gradient of the high-speed damping curve. While this is certainly an effective adjustment to have, it does mean that the shape of the damping curve at mid-range speeds can be altered quite a lot, and the shape does matter. Adding too much preload to clamp the shims closed also begins to add more damping at the low to medium speeds by extending the low-speed curve further, creating an increasingly digressive profile and a very high damping coefficient at the transitional velocities. There are limits to what can be achieved with this kind of adjuster, and again, it does a different kind of thing to altering the stiffness of a shim stack. Other high-speed adjuster designs used elsewhere, for example, include very large port orifice dampers in series with the rest of the damper circuits, which, if they're large enough to prevent excessive force at the high end of the velocity range, do very little at most other velocities, but if they're small enough to be effective across a wider range of velocities, generate extremely high forces at the higher velocities. This is because wheel compression velocities of somewhere between half to 1 meter a second are where we would typically consider the threshold between low and high speeds to be. But wheel velocities in compression are very frequently over 2 meters a second, routinely over 4 meters a second, and occasionally peak at over 8 meters a second. Due to the quadratic nature of port orifice dampers, the force generated is proportional to the square of the velocity, meaning whatever damping it's generating at 8 meters a second is about 4 times what it's generating at 4 meters a second, 16 times what it's generating at 2 meters a second, and 64 times what it's doing at 1 meter a second. Talking about force at the wheel here and using a rounded off conversion between kilograms and pounds of 2, if you wanted the high-speed circuit to give you, for example, an additional 5 kilograms or roughly 10 pounds of damping at 1 meter a second, you'd end up with an additional 320 kilograms or about 640 pounds at 8 meters a second. The reverse is also true. If you only want the high-speed circuit to generate 32 kilograms at 8 meters a second instead of 320, then at 2 meters a second you're only getting 2 kilograms out of it, and at 1 meter a second you're only getting half a kilogram out of it. In other words, basically nothing. Other attempts at directly adjusting the valving stiffness can be found in certain other dampers utilizing an adjustable lever arm for a leaf spring. But because all external adjusters require that the rider can turn them without jamming, they require a degree of clearance, or float, between the leaf spring and the shim stack that it supports. From a design and assembly standpoint, there is necessarily some degree of variation in the position of any two components that have to be set with clearance from one another and can't be clamped together rigidly, which in turn makes it difficult to ensure consistency between dampers because the distances that shims open during most movements are actually quite tiny. 100 microns is actually a moderately large opening distance for a shim stack. Changes in clearance as small as 10 microns can make large changes in damping force. Now, all this isn't to say that external adjusters aren't useful. They absolutely are, or we wouldn't have put them on the Telum. However, to the degree that any surface can ever be manufactured truly flat, there's no such thing as exactly flat, but it's easy to be extremely close for practical purposes. The real elegance of a shim stack is that it's easy for the elastic elements of the valve, meaning the shims, to have both zero preload and zero float, meaning that because of its zero preload, it can begin to open with even the slightest motion of the damper, and because of its zero float, it can be assembled in a very consistent manner, clamped together, generating a generally favorable and predictable characteristic that's quite linear. This is why it's the dominant valve mechanism you'll find across a massive range of mountain bike and motorsport applications, and why changing the shim stack stiffness has different effects to changing anything that we can do with typical external adjustments. Rapid Revalve is truly unique here. It lets us quickly, easily, directly, and consistently adjust the effective bending stiffness of the shim stack. In this sense, we might just have killed conventional suspension revalving. How exactly does the Rapid Revalve mechanism work? Check out part 4 of this video to find out.